let's have an example for partial derivatives. So here's a function. V of r and h is pi r squared h. And a prop, this thing. You guys tell me how this cylinder and that relate? Don't think too hard.
It's the area
That has the radius and
So that has r squared and height, so it'd be volume.
Yeah, so this is the volume of a cylinder of radius r and height h, right?
Yeah.
Okay, so my radius is the distance off the center, right? On the circle side. And the h is height of the whole thing, right? Okay, so we can take partial derivatives now because we just learned to do that. So can we take the partial of v with respect to r?
With respect to r, yeah. So h is constant.
Perfect. So we're going to treat h as though it's constant, right? And then we're just going to differentiate this formula with respect to r. So what do you get?
2 pi h r.
Okay. 2 pi r h. Right? That's really applying what?
calculus.
Yeah, that's Calc 1 idea of take the power down, right?
Yeah.
Not thinking super hard. Okay, what's this in terms of a cylinder?
Circumference.
Surface area?
Yeah, so that's the circumference times the height.
So cylinder.
Okay, so what does this thing tell you about? This should be the, how would you read this kind of in language instead of in math? So in math, I'd read it as the partial of v with respect to r, right? But in language, what does this mean?
The circumference of a cylinder at height h.
volume of the
This-
cylinder with
the
respect to its surface area.
The close. So the rate of change of volume with respect to radius, right? In other words, if I fiddle the radius around a little bit, how fast is the volume changing? Right? And I got the surface area? Does that make sense?
Mm-hmm. Yeah, because a little slice is the
Right.
thickness of its outside.
If you kind of fiddle the radius, right, you're going to make it just a little bit fatter, right? How much is the volume going to change by? Well, it's going to be just about the surface area, right? You guys see that? Another way to think about that would be to take your cylinder, cut it out, right? Unroll it into the poster that I really made it out of, right? And then think, what's changing the radius going to do? Well, that's going to do this to it, right? Fatten it up a little bit. And then when you fold this back around, you're going to get the change in volume, right? It's going to be that whole thing. So that's going to be the change in the radius, right? Times 2 pi r across the top, h on that side. And then you're going to say, okay, this guy is approximately 2 pi r h delta r divided by delta r, right? You see that kind of physical interpretation here? So, what about the other one? So, what's the other one?
partial v, partial h.
Partial v with respect to h. What's that going to be? Pi r squared, right? Right? Really, in the h direction, right? This thing is a line. This thing is a line, right? And it has slope pi r squared. So when I take the derivative, of course, I get pi r squared. What does that mean in terms of my volume?
It's the area
That's the area of
of
what?
the slice from that direction.
Yeah. The area of a slice is a good thought. I think there's a slightly more relevant one. I'm changing the height, right? So I'm thinking if I add a little bit in the height, how fast does the volume go up? So this is really the area of the of the top. You guys see that? Because of course, right, if I increase the height, the rate at which I'm accumulating more volume is however big the top is. Cool? Questions, things?
Confused. So why are we doing that last one in green? Where's that coming from?
Okay, so this thing depends on two variables, right?
Oh, so you're taking it from the first.
Yeah, so this V of R and H, that has two variables. So there's a R direction rate of change and an H direction rate of change. And I want to see what they both are. This is really just, for example, right? Here's a function of two variables. Let's compute both rates of change and then talk about them physically. So if I change the radius, I get the surface area as a derivative. And if I change the height, I get the area of the top as a derivative.
Oh, okay.
That's telling you, right, the rate at which you're accumulating new whatever as you change the bottom.
Because that's like usually a constant, and you can just get rid of it.
So I'm pretending the other variable is a constant. Okay, as I.
Oh, okay.
So here when I differentiated with respect to h, that was starting up here and saying, okay, everything here is constant except for h. What's the derivative I got? Well, I got the constant, and then I got
H should be 0.
h to the 0 is 1.